Hello everyone, my name is Dr. H.S. Madhusudan, Assistant Professor of Mathematics. Welcome to this video lecture. This is a BSc program of University of Mysore. Paper 3. Title of the paper is Algebra 2 and Differential Equations. And this is unit number 2. Here we study normal subgroups and quotient groups. In the previous session, we proved that if G is a group and H is a normal subgroup of G, then G by H is a quotient group. In this session, we prove some theorems on quotient groups. First theorem. Every quotient or factor group of a cyclic group is cyclic. That is, if G is a cyclic group and H is a normal subgroup of G, then G by H is quotient group. Now, in this theorem, we prove G by H is cyclic if G is cyclic. Okay? Right. Proof. Given G is cyclic, so therefore G has a generator. Let A be a generator of G. Let A be a generator of G. That means every element G belonging to G can be expressed as some integral power of A, where M belongs to I. So that is the definition of generator. Now also given H is a normal subgroup of G. Therefore, G by H is a quotient group. G by H is a quotient group. That is, what is G by H? G by H is equal to set of all elements of the form Hg such that G belongs to capital G. That is, it consists of all the cosets of distinct cosets of H in G. Right? Okay. Now we have to show that G by H is cyclic. So for that we have to find a generator. Now since A is a generator of G, we prove that HA is a generator of G by H, so that G by H is a cyclic group. Okay, so now we need to prove that HA is a generator of G by H. Now to prove this, first let us prove that for any integer m, H a power m equal to H a whole power m. Okay, so we prove it in 3 cases. First, case 1, Let m be equal to 0. Let m be equal to 0. Then what is a power 0? A power 0 is E, because A is a generator of G and it is cyclic. A power 0 will be equal to E, because every element of G is generated by A. So therefore E must also be generated by A, and we usually take A power 0 is equal to E, right? Okay. Therefore H A power 0 will be equal to H E, and that is equal to H, right? Now what can you say about H A whole power m? Whole power m, which is equal to what? H A whole power 0. Now H A is an element of G by H, because A belongs to G. Now consider the term, consider H A power 0. Then what is H A power 0? H A power 0 is nothing but identity element of G by H. And what is the identity element of G by H? It is nothing but H. We proved it in the previous session. So therefore in both the case, H A power 0 is equal to H A whole power 0. This implies H A power m is equal to H A whole power m. Now case 2. Let m be a positive integer. M be a positive integer. Then consider H A power m, which is equal to what? H A into etc. A. How many times? M times. Since H is normal in G, this can be written as what? HA into HA into HA. How many times? Again M times. So this is equal to what? HA whole power m. So therefore HA power m will be equal to HA whole power m. Here we are putting dot. This is actually star. Remember, this is actually star, that is binary operation of G. Okay, now case 3. Let m be a negative integer. Let m be a negative integer. Let m be equal to minus n, where n is positive. Okay. Now consider H A power m, which is equal to H A power minus n. But what is A power minus n? It is nothing but A inverse into A inverse into etc. A inverse. How many times? N times. Now see, when A belongs to G, A inverse also belongs to G. So A power n minus n is nothing but A inverse into A inverse into A inverse etc. N times. Okay. Now H is normal, and therefore this can be written as H A inverse dot H A inverse into etc. H A inverse. How many times? Again n times. So therefore this is equal to H A inverse to the power of n right? Now this is what? This is nothing but A inverse H. Because H is normal, HA inverse is equal to A inverse H. But to the power n. But this can be written as H A whole inverse to the power of n. Now this is equal to H A whole to the power of n into minus 1, which is minus n. Now this is equal to H A whole power minus n is nothing but m. Right? Okay. Therefore, in all the cases, we proved that H A power m is equal to H A whole power m. Now, let G belongs to capital G. Since G is cyclic and generated by A, G can be written as A power K for some K belonging to I. Now consider Hg, which is equal to H A power K, and that can be written as H A whole power K. So therefore, and Hg is what? Hg belongs to G by H. And therefore, every element Hg belonging to G by H can be expressed as some integral power of Ha. Therefore, Ha is a generator of what? Of G by H. Therefore, G by H is cyclic. Now, let us prove theorem number 2. It states, if H is normal subgroup of G and A is an element of finite order in G, then HA of G by H is also of finite order, and further order of HA divides order of A. Now proof. A is an element of G. A belongs to G. And order of A is finite, and let order of A be equal to n. Then A power n will be equal to E, where E is the identity element of G. Okay. Now H is a normal subgroup of G, and therefore H is a normal subgroup of G, and therefore G by H is quotient group. Quotient group. Since A belongs to G, HA belongs to G by H. HA belongs to G by H. Let order of HA be equal to M. Now we need to prove M is finite, and also we need to prove M divides N. Okay? Right. Now consider H A whole power n. H A whole power n. Now this is equal to what? H A power n. In the previous theorem we proved that for any integer m, H A whole power m is equal to H A power m. Now this is equal to what? H E. See here, A is of order n, therefore A power n is equal to E, and therefore H A power n is equal to H E, and this is equal to what? H. Now what is H? H is the identity element of G by H. Therefore, order of HA must be less than or equal to n. That is the definition of order of an element. So therefore, order of HA must be less than or equal to n. Since n is finite, order of HA is also finite. But order of HA is m. So therefore, m is less than or equal to n. Now let us prove m divides n. First, let us divide n by m. Now we can find two integers q and r such that n is equal to mq plus r with 0 less than or equal to r less than m. Now consider h, which can be written as h a whole power n, because here we have proved h a power n is equal to h a power n, and that is equal to h. Therefore, h can be written as h a whole power n. Now this is equal to h a to the power of mq plus r, and this is equal to h a whole power mq into h a whole power r, and that is equal to h a whole power m whole to the power of q, and this is h a whole power r. But what is h a whole power m? See, m is the order of h a. Therefore, h a whole power m must be identity element. But in G by H, identity element is h. So therefore, this is h whole to the power of q into h a whole power r. So if we raise an identity element to any power, it gives the identity element only. So therefore, this is h into h a whole power r, and h into any element, identity element into any element of G by H is again the same element, and therefore this is equal to h a whole power r. And we have started here and we ended up here. So therefore h is equal to h a whole power r, and this is a contradiction if r is less than m, to the fact that m is the least positive integer, such that h a whole power m is equal to h, because m is the order of h a. So r cannot be less than m. So therefore only thing is r must be equal to 0. So r must be equal to 0. Hence, from this we have n is equal to mq. N is equal to mq implies m divides n, and hence order of h a divides order of a. That completes the proof. Next theorem, let G be a group and let ZG be the center of G. If G by ZG is cyclic, then G is abelian. Now proof. First, what is Z? Z is equal to set of all A belonging to G such that A into X is equal to X into A for all X belonging to G. That is, A should commute with every element of G. So how do we form Z? Take an element A belonging to G and check whether A commutes with every element of G, then put it in Z. That is how we form Z. Now we have already proved that Z is a normal subgroup of G. Normal subgroup of G. Therefore, G by Z is quotient group of G. So we have proved that if G is a group and H is a normal subgroup of G, then G by H is a quotient group of G. Also given G by Z is cyclic. Therefore, there exists a generator for G by Z. Let ZG be a generator of G by Z. Now what we need to prove? We need to show that G is abelian. Let A comma B be arbitrary elements of G. Then ZA and ZB belongs to G by Z. Since G by Z is generated by ZG, every element of G by Z can be expressed as some integral power of ZG. Therefore, ZA will be equal to ZG whole to the power of some P, and ZB will be equal to ZG whole to the power of Q, where P and Q are integers. Now this can be written as ZG power P, and this can be written as ZG power Q. So now we have already proved that HA whole power N, HA whole power N will be equal to HA power N. Right? Now since A belongs to ZA, then A will be equal to some X into G power P, where X belongs to capital Z, and Since B belongs to ZB, comma, B will be equal to some Y into G power Q, with Y belonging to Z. Since X and Y belongs to Z, X into G power P can be written as G power P into X, because G power P is an element of capital G. And Y into G power Q will be equal to G power Q into Y. See, X and Y commutes with every element of G, and therefore it commutes with X commutes with G power P and Y commutes with G power Q. Now consider A into B, which is equal to, now A is what? X into G power P into B means Y into G power Q. Now using associative property, we can write this as X into G power P into Y into G power Q. Okay. And this will be equal to X into, now G power P into Y can be written as Y into G power P into G power Q. Now this will be equal to XY into G power P into G power Q. Now G power P into G power Q can be written as X into Y into G power P plus Q. So that is equal to XY into G power Q plus P, because P plus Q is equal to Q plus P, they are integers. Now this is equal to XY into G power Q into G power P, and that is equal to X into Y into G power Q into G power P here let us take this can also be written as Y into X into G power Q into G power P, and that will be equal to Y into X G power Q into G power P, that is equal to Y into X G power, now X commutes with G power Q, and therefore this can be written as G power Q into X into G power P, and that is equal to Y into G power Q into X into G power P. Now Y into G power Q is B and X into G power P is A. Therefore, AB is equal to BA. Now A and B are arbitrary elements of G, and we proved that A into B is equal to BA, which is nothing but commutative property, and hence G is abelian. I will end this session here. Thank you.